Welcome back. Today we're jumping into one of the most fundamental forces in the entire universe, electromagnetism. We're going to build a visual map, a way to make sense of these elegant, but let's be honest, kind of intimidating equations that run everything from our phones right up to the stars.
All right, so let's just dive right in. And you know what? We're going to start at the finish line, Maxwell's equations. I mean, look at them. These four super elegant lines of math, they are the foundation for everything. Your smartphone, the light hitting your face from the stars, all of it. This right here, this is our goal. This is our Mount Everest.
But okay, let's be real for a second. The path to really getting these equations, it can feel a bit overwhelming, right? We're talking about mastering over 50 fundamental equations and keeping track of more than 37 different physical variables. Yeah, it's a lot to take in.
But don't you worry, because there's a strategy for this. It's a game plan for tackling this mountain of information, and it's called Trinity memorization. It's actually a really powerful approach that connects three key ideas. First, you have to grasp the theoretical concepts, right? Then, you got to make sure all the math is consistent. And finally, and this is super important, you always check that the physical units, the dimensions, actually make sense. This is our toolkit for the climb.
So, to even start using our Trinity strategy, we first have to learn the language of this map we're building. And that language, well, it's all built around one incredibly powerful mathematical tool, a tool that's perfect for describing how things change in space.
And that tool is this guy right here, the nabla operator, represented by this cool upside-down triangle. I want you to think of it as a special set of instructions, like a probe you can use to explore a field. It is the absolute key that unlocks how electric and magnetic fields behave.
Okay, so you can use nabla in basically two main ways. First up, if we combine it with a field using a dot product, we get a simple number, a scalar. This is what we call divergence. Just think of it as a way to measure how much a field is spreading out from a single point. So if you get a positive divergence, you've got a source, like a sprinkler head. And if it's negative, you've got a sink, like a drain.
All right, so the second way to use nabla is with something called a cross product. And this time, instead of a number, we get another vector. We call this the curl, and honestly, the name says it all. It describes any kind of rotation or vortex motion happening inside the field. It's literally like stirring your coffee and seeing that swirl in the middle.
Okay, so why does all this matter? It all comes together in something called Helmholtz's theorem, and this is a huge idea. It basically says that any vector field, I don't care how messy or complicated it looks, can be completely understood just by breaking it down into these two simple parts: its sources, or its divergence, and its vortices, its curl. That's it. That one idea simplifies everything.
So, with that in mind, let's go back to our map and see how this all builds up into the complete picture. We can organize all of electromagnetism into a really neat structure called the EDBH-framework.
And here it is. This is our map. This awesome diagram connects the four essential fields in electromagnetism. We've got the electric field, that's E, and the magnetic flux density, B. Those describe the fundamental forces. But then we also have D, the electric flux density, and H, the magnetic field. These guys account for how those fields behave when they're inside different materials. And you can see this framework shows how they're all interconnected through those two ideas we just talked about, divergence and curl.
Now, take a look at this. One of the cornerstone equations on this map is that the divergence of B is 0. This isn't just some abstract math, okay? This has a really profound physical meaning. It tells us that magnetic fields don't have sources or sinks like electric fields do. Putting it another way, no one has ever found a magnetic monopole, a pure north or a pure south pole just by itself. It doesn't seem to exist.
And this is where it gets mind-blowing. This map holds one of the most stunning secrets in all of physics. See, the properties of empty space itself, its permittivity, which is epsilon naught, and its permeability, mu naught, they aren't just random numbers. Permittivity is basically how much empty space resists an electric field, and permeability is how well it supports a magnetic field. But when you combine them in this very specific way, you get the speed of light. Let that sink in. The speed of light isn't just about light. It's a fundamental property woven into the electromagnetic fabric of the universe itself.
Okay, so we've got our map. It's this beautiful theoretical framework. But how do we actually use it? How do we navigate the real world of circuits and antennas and electric motors with this thing?
Well, first off, never forget your most vital tool for the journey, dimensional analysis.
I know it sounds technical, but it's really just the simple act of checking your units. Volts, amperes, meters, at every single step of your calculation. Think of it as your built-in error checker. It's the thing that makes sure your equations actually make physical sense and aren't just nonsense.
And that leaves us with one final big question that's going to set us up for next time. This map, as powerful as it is, describes what's happening at tiny, single points in space. But that's not how we measure things, is it? We measure things over surfaces and along wires. So how do we connect this microscopic, point-by-point view to the macroscopic world that we actually live in and work with?
The answer, well, it lies in two incredibly powerful mathematical theorems that act as bridges: Gauss's theorem and Stokes' theorem. They're the tools that let us cross from our abstract point-by-point map to the tangible, real-world applications and measurements that we can actually use, and that is exactly what we're going to dive into next time.